If you haven't done so yet, please pause the video and attempt to solve the question on your own before listening on. Now we know that for a physical pendulum, the period of that pendulum is given by the following equation. The challenge in this case is to find the rotational inertia of this structure here. Now, the parallel axis theorem tells us that the rotational inertia of an object would equal the rotational inertia about its center of mass, which in the diagram would be this point right here, plus this term mh squared. Now, h would be the distance from the center of mass to the pivot point of the pendulum. We can see in the picture that the distance from the center of mass to the pivot point is marked as x. So, in fact, we can replace h with x. We also know that for a thin rod, the rotational inertia about the center of mass is equal to 1/12 times the mass times the length of the rod squared. Now we will notice that mass appears in both terms of this equation, so we could factor it. And so we are left with the following equation for the rotational inertia of this thin rod as it rotates about point O. So instead of just using I in the formula for the period, we're going to have to substitute in this entire expression in for that I. Now, after substituting in the expression for the rotational inertia I, we could see that the mass would cancel out in the formula. We also remember that h is the distance from the center of mass to the pivot point, and again, that distance is x, so we can plug in x for h. Now, if we wish to simplify this complex fraction, we can multiply both the numerator and the denominator of that complex fraction by 12. And of course, when we distribute the 12 here, it will cancel with that 12. And when we distribute here, it will make 12x squared. The bottom will just become 12gx. Now, we have the most simplified version of the period equation. Of course, to minimize the period, it would require us to use calculus and take the derivative of this equation, set it equal to 0, and solve. It's a little bit tedious to take the derivative of the entire right-hand side of this equation, so we can use a little bit of a trick. What we can do is simply take the derivative of what is present underneath the radical and set that equal to 0 and minimize that quantity. Because if we minimize the quantity in the brackets here, then we will automatically minimize the period t as well. So our task becomes to take the derivative of what's underneath the radical rather than the entire expression itself. So in fancy calculus notation, to take the derivative, we would set it up as follows. We're taking the derivative with respect to x. Technically, we have a quotient, so we're going to have to use the quotient rule. So we would have the bottom function multiplied by the derivative of the top. Now the derivative of L squared would be 0 since L is a constant. The derivative of this term would be 24x. So we would have 24x minus the top function, which again is L squared plus 12x squared, multiplied by the derivative of the bottom. Well, the derivative of 12gx would just be 12g. We just take the constant that's in front of the x. And then we have to divide by the entire bottom function squared, so 12gx squared. We'll set this equal to 0. Now, in order for the derivative to equal 0, only the numerator would have to equal 0. So we'll just set the numerator equal to 0. Now, there would be a number of ways to solve this, but perhaps what we can do is divide each term by 12g. And we would technically have to do that on the right side as well, but that will just remain 0. So the 12g would cancel here and here, as well as here and here. We'll then go ahead and distribute the minus sign into the parentheses. We'll then collect like terms, add the L squared to the right side, and then we'll divide by 12 and take the square root. We're left with a value of x equal to L divided by the square root of 12. L was given in the question, of course, so we could plug in. And when we simplify that, we get approximately 0.53 meters, and that indeed will be the correct value for x that will minimize the period. Now, in part B, to actually calculate the value of the period, we simply have to come back to our period equation. We'll plug in the value for L as well as the x that we just found in both the numerator and then the x also in the denominator. And when you carefully simplify that on your calculator, you get a period of approximately 2.1 seconds. And that is the correct answer. Thanks for taking the time to watch this video. If you liked it, please click the thumbs up button and also subscribe to the channel so you could stay tuned for additional videos. Also, you are welcome to send in your own question to the email address shown on the screen, and I will do my best to post a YouTube solution to it.